I welcome you all to the next in-series video lecture of EEE 615 Microcontroller Architecture and Organization. In this video lecture, we are going to see about registers, instruction set, significance of instructions, what are the different fields in an instructions, classification of microcontrollers, and in particular about 8051, its features, architecture, and functionalities. First, even in the theoretical lecture hour in the class, I told you about memory hierarchy, and I said as far as the entire memory structure is concerned, everything is a storage element, and just based on the location where they are called by different names. So the first and the foremost thing what we are going to see here is the registers. I've already told you registers are the closest to the CPU. Literally, they are inside the CPU. And what are the functionalities of the register? They are very vital for moving the data in and out of memory. So they act like a temporary storage, as I told you. They act like a temporary storage. They are very useful for internal transfer of data. I gave you an example in class, for example, swapping for ascending or descending. So that's a very good example of this internal data, transfer of data. But the problem with the registers is they can hold only pieces of data at times and not the entire data. For example, if you take 8051, I told you it's all 8-bit controller. So I told you all the registers will be of size 8 bits. So what happens is, if there is a 16-bit data or a 32-bit data, they cannot hold the entire 32 or 16-bit data at a time. They can hold only a 8-bit data per register. Probably if you want to store a 32-bit number, you need 4 registers like that to store your entire number. And in that case, you have to be very sure of the order in which you store, because LSB, MSB matters a lot. These registers are individually addressable. In the sense, all these registers, they have a pseudo name. For example, while programming in KL, we saw R0, R1, R2, up to R7 or R8. It doesn't matter, whatever number it is. This name is for your identification. But internally, they are all mapped to an address. So every register will have an associated address to it. So they are all individually addressable, not necessary it should be always as a cluster. So registers are individually addressable. Now, of all these registers that are available, not all are available for general data transfer. All are not available for general data transfer. Some are reserved for specific purpose, and these are called as special purpose registers. Okay, we'll see in future slides what are these special purpose registers. They vary from controller to controller or processor to processor. One important point to be noted is these registers are of high speed. When I say high speed, what am I talking about is the rate at which the CPU writes into these registers and reads from these registers are the quickest when compared to the other memory hierarchy present in the entire embedded system. Okay, and this I have been stating so many times, located inside the CPU and cannot be combined or confused with main or primary memory. Now, we were talking about some special purpose register reserved for some use, right, in the previous slide. This particular slide talks about some of the special purpose registers that you might find in general. One is program counter, accumulator. Accumulator is nothing but a special purpose register because it's a storage element, right? Except for that, we call it with a different name, accumulator. Stack pointer, instruction register, address register. Address register is nothing but the register which holds the address of the next instruction to be executed, or the jump or the loop address. Okay, index registers is definitely useful for index addressing, and a few SFRs, like some are bit addressable. Some are bit addressable. So these kind of SFRs are also present. Now let's look at the memory, we have spoken a lot about this memory. There are two kinds of memory: internal memory and external memory. Some controllers, they do come in with internal memory, and for some controllers internal memory may be absent, and we have to externally interface the memory. For example, if you take 8031, which is the I should call as a forefather of the 89C51, what we'll be programming or using now, has no internal ROM at all, but it has 128 bytes of internal RAM. Okay, it has got 128 bytes of internal RAM. Whereas if you take the case of 8051, it has 4K ROM and 128 bytes of RAM. I hope you all know the difference between ROM and RAM. Okay, ROM is a kind of a thing where you call it read-only memory. RAM is random access memory. Generally, whenever you design an embedded system, there are certain things that are not supposed to change or get altered because of the user. Those kind of stuffs are programmed or burned into ROM so that it never changes. Okay, something which can change or can be modified by the user are generally preferred in ROM. For example, if you take a microwave oven or a washing machine, what happens is the user has the privilege to choose different functions. Okay, but once a function is chosen, there are certain parameters that are fixed for that function. For example, if I choose a normal wash in a washing machine, I have the liberty to choose between normal or heavy or light. Okay, but once I choose normal, there is something called water level, there is something called detergent level, there is something called spin time, rinse time, wash time, that are internally associated with the washing machine, which will not change. So I cannot alter those things. All I have the facility is to choose the function, choose the cycle of wash. Once I choose the cycle, the parameters associated with the cycle cannot be changed. So for example, if you take mathematical calculation, the value of pi is constant. It cannot be altered, or it should not be altered, even by mistake. So those kind of stuff where you don't want things to change are written in ROM. Okay, so that's the basic difference. Now, I've already spoken about this in class. CPU architecture can be classified into two types. One is accumulator based, where I already told you accumulator should be one of the operands in any mathematical or logical operations. These are some of the characteristics of this accumulator based architecture. As I told you, accumulator based machines or processors or controllers are also called as one operand machine. Why this is called as one operand machine? Because accumulator is already part of the instruction as one of the operand. I already told you instruction set has a minimum of 3 fields. One is the instruction, one is operand 1, one is operand 2. Okay, since A in this particular architecture, accumulator, or what we call as A, is fixed as one of the operand, all you need to specify is only the other second operand. Okay, so since that one operand is fixed, it's called as one operand machine. It's a very simple architecture. I told you the contents of the accumulator will participate in all kind of operations. Okay, instructions take less cycle time as far as accumulator based architecture is concerned. For example, if you see here, load A loads accumulator with the contents of the register A. Okay, add B, it adds the accumulator content with B, and the result is automatically stored in the accumulator. The next type of architecture what we see here is nothing but register based architecture. Now in register based architecture, what we have is excuse me, in accumulator based architecture, whenever you want to load a data, automatically all you do is move or move immediate or move C or move X, depending upon whether it is from external memory or internal memory, or it's an immediate data or direct addressing or indirect addressing, or from the data memory, something like that, data internal memory. But whereas a register based architecture, if you see, the conditions is, as I've discussed in the class, it's not necessary accumulator should be part of an instruction. It can be between 2 registers as well, as you see in this particular example. It can also be between two registers. But the only issue is, as a user in accumulator based architecture, you don't have to worry about where the result is getting stored. But whereas in register architecture, it is the responsibility of the user or the programmer to make sure that this kind of store command is being used to make sure the data is safely returned back to the memory or in a location so that the result is safe. Okay, generally if you take register based architecture, they are best suited for RISC based machines. I'll tell you shortly what is RISC, what is CISC. Generally RISC is nothing but reduced instruction set machine or reduced instruction set computer. Generally register based architecture are best suited for RISC based machines. Okay, now we have already spoken about instructions. I'll just go over it quickly. It provides 4 information to the CPU. The first information is operation to be done or opcode. That's how we get the name opcode, operation code or instruction. That's the first information that it conveys, operation to be done. The second information what it conveys is the operand on which the data operation has to be performed. Operand 1, operand 2. I already told you either it can be directly given or as an immediate data or through addressing, which is called direct addressing or even indirect addressing. Fourth one, not necessarily in all cases, but in times, the result address where the result has to be stored. That's another information the instruction has to convey. In some architecture, everything is covered in one single instruction, whereas in few architectures, first the operation has to be performed in one instruction and the storing has to be performed in the other instruction. So this covers, encompasses everything, not necessarily the instruction should be always like this, okay? And finally, the next instruction address, so that the next instruction can be fetched, decoded and kept ready for execution. So these are the 4 different informations provided to the CPU by the instruction set or in the instructions, not necessarily or comprehensively including all the 4 fields. Sometimes it could be just these 3 fields, or it could be 4, or it could be all the 5 different fields. Okay. This is something that I've already gone over, so I'll just keep the slide for a few seconds so that you can take a look at it. Operands can be, how this particular slide talks about how the operands can be specified by the instruction, and this is the example what we have here. This is nothing but immediate data. You see the hash symbol here. Whenever the hash symbol appears, what it indicates is the number followed by the hash symbol is the data. Okay, direct data. And I've already told you H indicates hexa. If you don't put H, it's decimal. And if you write it in binary, for example, this 34 number would be written as 0011 and 0100B. So if I'm planning to write it as binary, I should put a hash symbol. I should write this will be 3 and this will be 4, button by B, which indicates binary. So if I don't put H, it's decimal. If I put H, it's hexa. If I write its binary equivalent and write it with a B, it's binary. Okay. So these are the 2 examples. Okay. This is from register to the accumulator. This is from an address location to the accumulator, and this is immediate data. Similarly, the result address, in case of accumulator based architecture, we don't have to worry about the result address because it automatically goes to the accumulator. In case of register architecture, it's very important for us to tell directly or indirectly the location where the result has to be stored. For example, in this particular case, if you take a look at this particular instruction, it says add R1, R2. Okay, assuming something is internally specified, what it indirectly states is conveys is update the content of R1 with the result of R1 plus R2. So initially R1 had 2, let us assume R1 had 2 and R3 had 3. So now R1 is equal to 2 plus 3. So the new value of R1 will be 5. You get it? This need not be all the case. Sometimes instructions will not allow you to do this in certain architecture. So what we have to do is we have to say add R1 comma R2, then store R3 comma R1. So what here happens is the register contents are not replaced. R1 remains as R1, R2 remains as R2. And the result we are asking to shift to R3. Sometimes the same instruction set can also be written like add R3 comma R1 comma R2. Here R1 and R2 are added and the result is stored in R3. Okay. This is just an example of a 16-bit instruction set. This particular example, what it conveys is the instruction size is of 16 bits and how the fields are divided. Okay, so you have allocating 4 bits for opcode, 6 bits for specifying operand 1, another 6 bits for specifying operand 2. So what do you mean by 4 bits allocated for opcode is nothing but, I told you ultimately everything is going to be converted to binary, right? So what is the maximum number of bits that can be used to represent opcode in binary? Okay, for example, for add, it could be 0001. This is just an example, okay? Don't take it literally. And for mul, it could be 0010. And for div it could be 0100 something. Okay, so whenever the processor encounters a mul, this will be converted into this kind of binary number. So how many bits can be allocated to present opcode? So here the data 1 or the operand 1 can be maximum of 6 bits. Again, it is for about 6 bits. So if you are going to use an 8-bit data here, it's going to give you an error or it cannot be processed. Okay, so it's going to give you an error. So the data should be less than 6 bits. Not necessarily in every architecture it should be the same way. For sometimes, it could be like 2 bits for opcode, 7 bits for operand 1, and who knows, 7 plus 2, 9. So it could be another 7 bits for operand 2. That is also possible. Okay, or it could also be 6 bits for opcode and the rest divided between operand 1 and operand 2. So it all depends upon the ISA or the designer who has designed the ISA. It can vary from processor to processor, controller to controller. Now we have to know about a particular technical jargon. If I'll just go back to the previous slide. So in this particular example, if you see, the instruction length is of 16 bits. Okay, now when I say instruction length is of 16 bits, all instructions, whether it is add, mul, div or whatever it is, all instructions are 16 bits wide only. All instruction length are 16 bits wide only. For example, even if I use a no op where there is no operand 1 or operand 2, the entire 16 bits will be used for representing no op. For example, for no op, so let's say the opcode is represented binary representation of 0. Okay, it's enough if I use just a 1-bit field to represent no op. But since here the length of the instruction set is fixed, what will happen is no op will be represented as 0, 0, 0, 0, 0, 0, 0, 0, 0, ... So this will be 16 zeros. We are unnecessarily wasting space or memory. Okay, so this is called fixed length. No matter how many ever bits you need for representation, 16 bits will be totally available for you, and you cannot change anything here. Once the size of the opcode representation, number of bits for operand 1 and operand 2 is fixed, this is going to remain fixed. For example, if the data what I'm going to add is only of 2 bits, still 6 bits will be used. The remaining 4 bits will be filled with zeros. Here we are unnecessarily wasting space. So this is fixed length instruction set, and this is the disadvantage of fixed length. So they went for a variable length. What do we mean by variable length is, depending upon the operand size 1, operand 1 size, operand 2 size, and opcode bits representation, this particular wall, what you see here, I will call this as wall, okay, or the delimiter or the barrier. whatever it is. This, instead of being rigid, is flexible. That means, for example, for one particular data operation, if I need only 2 bits to represent opcode, this particular wall can be moved from here to here, so that more bits can be used for accommodating data. Similarly, if the instruction is complex and data requires only 3 bits for that particular operation, I can move this wall from here to here. Similarly, I can have different data lengths between operand 1 and operand 2. So this is the advantage of variable length. But variable length also has its own disadvantage, in the sense the decoding logic becomes very, very complex for variable length as opposed to fixed length. Okay, for example, if you see in fixed length, let us take the same example. 4 bits are used for opcode. So whenever the instruction set goes into the decoding mode, always the first 4 bits are translated into the respective operation that needs to be performed. The next 6 bits are considered as data 1, and the next 6 bits are considered as data 2, upon which the operation has to be performed. But when it happens to be a variable length, you see this is going to vary from instruction to instruction, data to data. So the decoding logic becomes very, very complex. You cannot, just like that take the first 4 bits always for opcode. Sometimes it could be the first 2 bits as well, the MSB, and the next bit to the MSB could be for the opcode as well. So here the decoding logic very complex. So this is the problem with variable length coding. Now, there are 2 types of instruction sets that are possible. Remember, I told you in one of the slides that, register architecture suits best for RISC-based machines. There are 2 types of instruction set. One is called RISC, one is called CISC. What is RISC is reduced instruction set computer. CISC is complex instruction set computer or machines. Okay, so what is this CISC? What is this RISC? We'll see it now. Now, in CISC, most of the instructions are variable length instructions, whereas in RISC, if you see, it's a single word or fixed length. Now, what is the advantage of the single word or fixed length is, most of the instructions can be run in one cycle itself. Okay, the advantage of having the RISC is, most of the instructions can be run in one clock cycle itself. Okay, so that is why we call it single word instructions. Now the format is variable, here the fixed field format. Again, these two are related. What I mean by fixed field format is, the field length can be varied here, the field length cannot be varied here. What do I mean by field length is, I told you, right, for some operation I might be using only a 3-bit data, for some operation I'll be using a 8-bit data. So the intermediate barrier I was talking about, the wall, I told you that will be flexible, right? So that is what is meant here, variable and fixed. Now if you take CISC, lot of instructions will be based on memory operands, whereas if you take RISC, it will be more of a load store architecture. Okay, here in CISC, one of the advantage what we have is complex operations can be performed using single instruction. Okay, whereas in RISC, you see the complex operation cannot be performed in single instruction, but it has to be a combination or multiple instructions to perform that operation. So what does it indirectly indicate? In CISC, the code density will be less, or the code length will be less compared to RISC. That is what it is indirectly stating. Now if you take other differences between CISC and RISC, as I told you, complex instructions can be performed in one single instruction. So because of that, I told you the code size decreases. So the primary goal of CISC is to complete the task in as many fewer lines as possible. That is the main objective or the bottom line of CISC. The primary goal is to complete the given task in as much of fewer lines as possible in the coding. Okay, whereas if you take RISC, the primary goal is to speed up individual instructions. Speed up individual instructions. Now please go back and remember what I taught in the class or in the video lecture. I have taught you certain parameters that are that has to be looked into before choosing a processor, and there is one parameter that is associated, or it has been elaborated here. So just go back and remember what property or parameter is that and relate it to this particular definition. Okay, the primary goal of CISC is to reduce the code density, whereas the primary goal of RISC is to increase the speed of execution of individual instructions. Okay, in CISC the emphasis on hardware, and in RISC the emphasis is on software. Okay, multi-clock complex instructions, single clock instructions only. This is what I was saying. Since it is a single word, simple instructions, all instructions, I shouldn't say all, most of the instructions can be executed in one clock cycle. Whereas this being complex, it will take multiple clock cycles for one instruction to get executed. So we cannot say CISC is bad, RISC is good, or RISC is bad, CISC is good. Each has its own pros and cons, and we should be wise enough to choose, which kind of instruction set are we going for what kind of applications. This I already discussed in the class, von Neumann and Harvard architecture. Now, one more thing I want to tell you is von Neumann is also sometimes called as Princeton architecture. Okay, so I told you, as far as von Neumann is concerned, address bus and data bus are unified. That is, or I should say, in memory, program memory and data memory are the same. There is no classification between program and data. Everything is being dumped into the same memory. So that's von Neumann, and you have the same buses for it. And whereas in Harvard, if you see, you have a different memory segment for program and a different memory segment for data. So an instruction can be fetched, and simultaneously the necessary data can also be fetched, thus increasing the level of parallelism in Harvard architecture. Whereas in von Neumann, whenever instruction is being accessed, data cannot be accessed, or whenever data is being read or written from, the instruction cannot be retrieved or read or read from the memory. So the level of parallelism is reduced in von Neumann as compared to the Harvard architecture. Now we are getting into the actual concept of microcontrollers. So what is this microcontroller? If you look at a book definition or a typical scientific definition, microcontrollers are nothing but a chip that contains several dozens of general purpose IO pins, which can be configured through software as input or output, and it has got some extra accessories apart from the basic processor for computational purpose, and apart from those peripherals or accessories, it also has internal memory. So indirectly, what is this definition trying to tell you is a microcontroller is equal to basic CPU plus internal memory plus some peripherals like timer, interrupt, etc. plus GPIO. GPIO is nothing but general purpose input output pins or ports, which can be configured through software as either input or output. So this entire package is what we call as microcontroller. So what could be microprocessor? Microprocessor is nothing but same as microcontroller, except for that it will have only the CPU. It will not have, of course, it will have the pins for external peripheral interface, but this will not be there. The internal memory, peripherals, timer, interrupts, nothing will be there. It will be just the CPU with couple of CPU registers and input output pins. That's it. So this is basically microcontroller. This is basically microprocessor, and that is the basic fundamental difference between a microprocessor and a microcontroller. Now, if you look at the graphical definition of the microcontroller, whatever we have seen before, this is what it has. It has got a general purpose CPU. It has got some RAM, ROM. I was talking about internal memory, right? IO port, timer. It has got its own address bus, data bus. So this is the graphical definition of a microcontroller. Okay. Now, microcontrollers can be classified on so many aspects. Okay. So we can't say, this is how microcontrollers can be classified or divided into. They can be classified based on the bits of operation. When I say bits of operation, I'm talking about data bits, based on the memory it has, based on the instruction set it carries, and based on the memory architecture. Okay, if you take the bits, microcontrollers can be classified as an 8-bit controller, a 16-bit controller, or a 32-bit controller. I've already told you 8, 16, 32 are nothing but the bits of data that can be handled at an instant or simultaneously. So based on that. Now based on memory, we can talk about either embedded memory or external memory. When I say embedded memory, remember in 8051 I told you there is 4 KB of flash, okay, 128 bytes of RAM. So those are called embedded memory. It comes with the chip or the controller itself. External memory is some controllers may not have internal memory and you have to externally interface. So based on that, there can be two classifications. Okay. Again, as far as instruction set is concerned, we have three categories. Two major categories that you're already familiar with is CISC and CISC and RISC. There is one third category where CISC instruction set implemented on a RISC-based core. RISC-based core, and based on memory architecture, Harvard, Princeton. Okay, you get it? Now, as far as this memory classification is concerned, off late we can add one more set of classification. One is called ASIC. Okay, application specific integrated circuit, where once you design, the functionality is fixed. And the second one, what I can call is FPGA, or field programmable gate arrays. We can even extend the technology to SoC, system on chip. So again, based on the way the microcontroller is created or constructed or designed, it can be either a ASIC or a FPGA or SoC based type. Okay, these are different vendors. Okay, ARM, Texas Instruments, Hitachi, PIC, Motorola, Intel. They have so many vendors, manufacturing different kinds of microcontrollers. So this is how the microcontrollers are classified based on bits, memory, instruction set, memory architecture. Now, what are the parameters that one should look into while selecting a microcontroller? Okay, programmability and reprogrammability. What does it mean? How many times the microcontroller will allow you to program or reprogram itself. For example, the 8031, the ancestor of 8051 or 89C51, whatever we are talking about, when we see this, it can be written only once. The program can be written in this only once. Suppose you make a mistake, you write the program wrongly, this is a throwaway. Okay, whereas 89C51, it allows you to rewrite the program probably maximum for 1000 times. Okay, so you have to check how flexible the processor you are choosing is, so that it allows reprogrammability or programmability. Next is throughput. Next one is peripherals. For example, if I'm going to use my embedded application in an environment, in a power plant, where I'm going to monitor the temperature of a boiler or a temperature of a generator or an alternator, whatever it is, the measuring quality, the measuring parameter or the measuring quantity is going to be analog. Now I want to convert it to digital, so definitely I need an A to D converter. So as a designer, rather than going for an external A to D converter, I'll generally prefer an A to D converter which is inside the microcontroller, so that I can easily program it the way I want. So this is one just example of what kind of peripherals I am looking for in the microcontroller, what I want to buy. Next is physical packaging. There are different types of physical packaging like DIP. DIP is nothing but dual inline package. It's the normal ICs, what you see, with pins which can be fitted into the breadboard. But off late, even SoC based physical packaging comes, where you cannot use a soldering iron to solder the component to the board, or you cannot put it on a breadboard. It has to be machine soldered, and it has to be a very fine soldering. Okay, so depending upon the facilities available here and the size of the component you need and kind of packaging, you have to go for a physical packaging. Similarly, memory. When I say memory, I'm talking about you have either you want an embedded memory or an external memory. or if embedded memory, what should be the size of embedded memory in your microcontroller and so on. Then latency, this is very, very important. What do you mean by latency here is the response time of the processor to the IO devices. Okay, for example, if I'm asking you for a glass of water, you can either get it to me the next instant, or you can get it to me after 5 minutes, or you can get it to me after 10 minutes. So whom do you think will I prefer? The person who gets to me the next minute. So latency or the response time is very, very important. It is the reaction or the response of the microcontroller to the IO device request or the interrupts request. Okay, generally lesser the latency, better it is. Now we are going to very specifically now talk about MCS51 or 8051. Okay, 8051 has a Harvard architecture. Okay, it's a single chip microcontroller and it's of size 8-bit. So it's a 8-bit Harvard architecture single chip microcontroller. Again, when I say 8-bit, at an instant 8051 can handle only 8 bits of data or a byte of data. Now this particular table, what you see on the slide, talks about the history of or the evolution of the current 89C51s what we are using. So this is the front runner or the forefathers of all these what has been developed of late. So how many pins it has, what kind of on-chip memory, what kind of on-chip data memory or program memory, number of IO lines, number of timers, serial interface, what kind of serial interface, whether it has or not. All these things are given in the table. So at your leisure, you can just take a look at it. I'll leave the slide for some time to stay, so that you can just browse through to understand the difference between different versions of 8051. That's what I should say. Even though these things vary, the architecture and the ISA remain the same. Okay, the architecture plus ISA. ISA is nothing but instruction set architecture remains the same. Now this is the architecture of 8051. Okay, so it has got 4 IO ports called as P0, P1, P2, P3, 4 IO ports. It has got a serial port, so it will obviously have a transmission and a reception pin. It has got 2 timers, timer 0 and timer 1. Now this timer 0 and timer 1 can also be used as counters. And if you look at this, there are various modes for using these timers. I can use these timers as 16-bit timers, 8-bit timers, counters. Again, if you look at the 16-bit and 18-bit mode timer, I can use it as either auto reload or manual load mode. Don't worry, just try to get this into your head. We will discuss all these things in detail. Okay, so it has got 128 bytes of RAM, 4K of ROM. Okay, so it has got an interrupt control module. So it has got 3 internal interrupts and 2 external interrupts. The 2 external interrupts are nothing but INT0, INT1. These are the 2 external interrupts. You have the actual CPU. This is the oscillator. Generally all 8051s are supposed to run at 12 megahertz, or to be precise 11.0592 in general. Okay, but there could be variation where some could run at 22 or 24, something like that. Okay, this is the bus control. Okay, it basically controls the bus, where, when, what should be placed in address bus and data bus. So this is the general architecture of 8051. In the next video lecture, we will discuss in detail about what are these 4 IO ports. Are they unifunctional or multifunctional? How are they addressable? Okay, what are these interrupt? I told you there are 2 external interrupts, INT0, INT1. What are the internal interrupts for? How are they connected? What is the interrupt service routine, ISR? What is this timer? How they can be configured in different modes? Different control registers associated with each of this. All of this we'll discuss in the next video lecture. Thank you.